So the last part of section 11.2, we're going to take a look at adding up numbers in a sequence again. So we're going to be looking at a series, but this time we're going to be adding up infinitely many numbers. So at first you might think, well, how can you add up infinitely many numbers and have it actually get an answer? Because if you add up infinitely many things, doesn't it just get bigger and bigger? And the answer is no, not always. Okay, so we're going to look at, first of all, when can you actually add up numbers and when can't you? That's the first thing you have to figure out. And then if you can add up infinitely many numbers, then what's the answer? So we'll look at that. Okay. So that's basically what I just told you. So if you want to write adding up infinitely many numbers, we're going to kind of borrow the notation from yesterday, but what's going to look different is the top on this sigma. So yesterday, we always had a fixed value on the top. Whether you knew the fixed value or you didn't, it was a fixed value. Today, what's on top of the sigma is an infinity symbol. That represents starting at 1 and adding up infinitely many terms. When you write it in the expanded notation, what tells you in the expanded notation that it's adding up infinitely many terms? Yeah?
The dot, dot, dot.
Which one?
The one at the end.
The one at the end. Yeah, the dot, dot, dot in the middle just means there's a bunch more terms I'm not including. The dot, dot, dot at the end means there's a bunch more terms I'm not including at the end, so it goes on forever. So that's how you write an infinite summation using sigma. So adding up an infinite amount of terms by hand, obviously you can't do that. Right? It would take a long time. So we've got to figure out a different way to add up infinitely many things. Right? And we're going to do a little bit on the calculator in terms of like a visual, and then we're going to look at a formula. So the idea of adding up infinitely many things is kind of like the idea of an asymptote. It's a value you're going to get close to, but you never reach. So if you were adding up infinitely many things, and there was a number that you could find, okay, let's call that number S. S stands for sum. So if you could figure out some number that you think infinitely many things add up to, and you draw a horizontal line at that number, and then you draw your sequence. Remember, the sequence would look like a set of dots. It would not be connected because we talked about how there's nothing between the first and the second. Right? So if you had a series of dots, and they started to look like this, each one of these dots represents a partial sum. S1, S2, and so on. Remember, a partial sum is the sum of every single term up to that number. Sum of the first 2 terms, first 3, first 4, first 5, first 6. If we were to keep adding up terms, and we did like the first 100, it looks like the red dots are getting closer and closer to this horizontal line. If that's true, and the red dots just get closer and closer and they never cross it, then this line right here is an asymptote that represents the sum. Okay, you found it. We have to talk about how you find that, but that's the idea. And what we say is that the sequence of partial sums is convergent. That's the word you use. Converging means that something is getting closer and closer to a number. It's never reaching it, but it's getting closer to it. When we talk about converging, we can talk about sequence converging, or we can talk about the series converging. Okay? That's 2 different things. Here's an example of a sequence, like from Monday, converging. If I were to continue that sequence forever, the individual terms in that sequence are approaching a value. What are the terms in the sequence approaching? Yep.
0.
The terms are approaching 0, right? They're getting smaller and smaller and smaller. This is the kind of sequence that you could add up infinitely many items in that sequence, and you would get an answer. And the reason you would get an answer is because the individual terms you're adding are getting smaller and smaller. So think of it as eventually these terms get so small, when you add them, they don't even make a difference anymore. Even though there's infinitely many of them to come, they're infinitely small, so they don't make a difference. So by the end of today, you'll know what all of this would add up to. This one would actually add up to I'll show you after. It's actually the formula for finding what this adds up to is easier than the one we did yesterday. It's a little bit shorter. Okay, so any question on the idea of this sequence converging? Okay. Let's look at the next thing. So when we look at an infinite sum, we're not really looking at the sum itself, because that's impossible to add up infinitely many things. What we're looking at is this. We're looking at the sequence of partial sums, but we're just going to look at it really, really far away. Right? If we can add up the first 500 numbers, and it looks like we're getting very close to a number, then that's pretty much what it's going to be if we were to continue adding up the first 5,000 numbers. In fact, you're probably going to be able to add up like the first 4 or 5 numbers, and you'll be able to tell from that what all of the numbers would add up to. Okay? So we're going to be looking at a sequence of partial sums, and we're just going to look at it way out, far out, and then that's going to tell us what it adds up to. Okay? So kind of looking at something that's like an asymptote. Okay, so this is the formula specifically now for an infinite geometric series. This comes from what I showed you on Monday, a sub 1 times r to the n minus 1. That's always the formula you use to generate terms in a geometric series. The first term is what you would get when you fill in 1, because it's telling me to start at 1 for k. Well, if I fill in a 1 right there, I end up with r to the 0. R to the 0 is just 1. And 1 times a to the 1, a to the 1. For this term, you would fill in a 2 for k. When you fill in a 2, you get 2 minus 1 is 1. R to the first is just r times a to the 1. So what happens each time is the exponent on r is going to keep going up 1. Because k keeps going up 1. But the exponent is always going to be 1 smaller than the position. Position 1, position 2. And the reason the exponent is always 1 smaller is because of that minus 1. So let's do, it's kind of a review from yesterday a little bit, but let's take this geometric sequence and let's add up the first 4 terms, then we'll do the first 5, and then we'll do the first 6. And the goal is I'm trying to look at what's happening as I go further and further out. And I want to see if I'm approaching a value. Okay, so can somebody remind me from yesterday, what's the formula, was the last formula we did, for the sum of a finite geometric series. Yep.
A1 times 1 minus r to the n.
Yep. 1 minus r to the n
And then 1 minus r.
over 1 minus r. So let's do that for this sequence, and let's do the first 4. Okay. If I'm finding s sub 4, what letter is the 4 going to be in that formula? Charles?
N.
Yep, that's going to be my n. What number am I going to fill in for my first term? What is a1? If you're not sure what a1 is, fill in 1 for k, and then that's your first term. Yep.
That'd be 0.
No, if you fill a 1 in for k, you will not get 0 from that formula. Yep. 2. Yep, you'll get 2 times 1, which is 2. So our first term is a 2. Our n value is going to be a 4. And what's the r value? That's what you're multiplying by each time to get to the next term. But if you know the structure of your formula, the r value is in your formula. Yep.
The common use here.
Yep, which is, in this case, how much? Yep. 1/3, right? The r value is always, it's a sub 1, r to the n minus 1. So your r value is right next to a1. So now, fill in 1/3 for r. Okay, so I already did that. First term is 2, r is a third, and I did it when n was 4. When I add up the first 4 terms, okay, I don't even know what the first 4 terms are. I didn't even find them. I just found what they added up to. So I don't even have to know what they are to add them up. That's the advantage of this formula. The first 4 terms add up to 2.96. If I add up the first 5 terms, you can see that the 5th term in this sequence isn't very big. It only added about 2/100ths, a little over 2/100ths to the previous number. So we got 2.9877. And if we add up the first 6 terms, we get 2.9959. Now, if you didn't want to have to calculate those by hand, you can put that into the calculator as a formula. You would want to type this in. You are going to have to use x instead of n as your variable. So let's put all that in and see if we can calculate those values using a table, just in case I say, like, I want you to tell me what's S4 through S10. Well, that's going to take forever if you're going to keep typing them in like that. Well, let's do it on a table. All right, so first of all, you're going to need parentheses. So we're going to have a 2 on the outside. I'm going to do a parenthesis for my entire fraction. And then I'm going to do another parenthesis just for the numerator. 1 minus 1/3 to the x. And that finishes my numerator. And if we want to make the denominator simpler, then just type it in as 2/3. 1 minus 1/3. So divided by 2/3. So that's your denominator. Bless you. And then close your fraction. And I think I need to close one more to keep that 2 on the outside of everything. I might have an extra set of parentheses, but that's okay. All right, now let's go to the table. And
What's the extra parenthesis in the end?
I do, yeah, I thought I might have had an extra. So remember, when you start plugging in values, the only ones that are going to make sense are values that are integers. Okay. I still don't think I put that in right. Let me check it. 1 minus 1/3 to the x divided by 2/3 times 2. Second table. 2. Oh no, I did type it in right. Okay. So if you add up the first term, you get 2, because the first term is a 2. If you add up the first 2 terms, you get 2.67. If you add up the first 3 terms, that's what you get when you add up the first 4 terms. That's what we did. The first 5 terms, and then the first 6 terms. If you add up the first 20 terms, it already says you're at 3. Now, is that really a 3? No, it's just extremely close to 3. But that's not even adding up that many, right? Just adding up the first 20 terms, if you generated every number by plugging in 1 through 20 for k, and then adding them all up, you're already at like 2.999999999. So you're getting very, very close to 3. For this particular problem, we would say 3 is the limit of the series. Okay, 3 is called the limit. It's what you're getting closer and closer to. You're never reaching it, but it's what they would all add up to if you could add up infinitely many numbers, 3. And the reason this works is because each time you add a new number, it's 1/3 the size of the number before it. So if you keep multiplying a number by 1/3, it's getting smaller and smaller and smaller. As long as what you're adding each time is getting smaller, it will add up to something. If what you're adding each time gets bigger, like let's say you double, instead of multiply by 1/3, that's not going to work. If you add 2 plus 4 plus 8 plus 16 plus 32, it's just going to get bigger and bigger. All right, so we got to make sure if we're adding things to infinity, are we adding something that's getting smaller each time? All right, so let's visualize what that would look like. So I've already typed it all in. That's what we just went through. Okay, I can hit graph. And the calculator, when you hit graph, it doesn't know, first of all, that you only want to graph numbers from 1 and up. And it doesn't know that it shouldn't be connected. Right? So what this graph should really look like is just a set of dots. If you add up the first term, you get 2. The first 2 terms, the first 3 terms, 4 terms, and so on. Right? So it should just be those purple dots. There's no way you can add up 2.5 terms. You add 2 or you add 3. There's nothing in between. And now, again, focusing on positive integer values, not negatives, not decimals. If I put a line at y equals 3, and it looks like that red curve is getting closer to it, then 3 is the sum. And yeah, it looks like it actually touches it. It never does. But that red curve is just getting closer and closer. So because I found a horizontal asymptote for that graph, the horizontal asymptote is the sum of all the numbers to infinity. Right? That's how you can think about it visually. So technically, you never reach it. But as you head towards infinity, that picture is a good approximation of what's happening. Okay, so any question on how that picture is showing you that the answer to adding up infinitely many terms in the sequence I just wrote down is 3? And we just did example 2. That's exactly what I just did a picture of. So find the sum using a graphical approach. I did it right there. Okay, let's try this one. 4 times 3 to the k minus 1. So the idea is we'll look at what happens when you add up like the first 5, the first 6, the first 7, and see if you notice if you're getting closer and closer to something. Okay, so we've got our formula. A sub n, S sub n equals A1, 1 minus r to the n, over 1 minus r. What is going to be the first term if you plugged in k equals 1 in that sequence? Yep, 4. So 4 is the first term. And what is it that you're multiplying by each time to get the next term? Yep, 3. So let me list a few terms out just so you can kind of see what it looks like. So this is, first term is 4. If you plug in 2 for k, what would your next term be? Yep, 12. Yep. And if you plug in 3 for k, what would your next term be after that? Yep, 36. And so on. You're just multiplying by 3 each time. So I'm going to put that formula in on the calculator, just like I did last time. I'm just going to change the first term and the r value. Now, we can figure them out before we even use the calculator. If you add up the first one term in that sequence, what do you get? Yeah?
4.
So S1 should give me 4. What's S2? Yep. 16. And what's S3? Yep. 52. Okay, now I might ask you what's S sub 500 on the test. You don't want to do it that way though. You want to do it this way. Okay. Plug it in and use the calculator to find the value. All right, so this time the first term is 4. My r value is 3. And my denominator is 1 minus r. That's negative 2. Okay, so just make sure I fixed everything right. First term, 1 minus r to the n over 1 minus r. Since we did the first 3 terms, we can check it and make sure we get those answers. Yep, I don't know if you can see it or not, but when you plug in 1, you get 4. 2 gives you 16, and 3 gives you 52. Yep. So we know we have it right. So now I want to look at what happens if I keep going. If I add up the first 4 terms, first 5 terms, 6 terms, first 20 terms. What's happening to my sum in this case? Yeah? My sum is approaching infinity. This is not converging. Right? This is what we call diverging. I'm not getting closer and closer to a value, a number. Infinity is not a number. Okay? So in this case, where it says find the sum, you would say this one, it diverges. There is no sum. So this is what we call divergent. You can say it diverges or it is divergent. And the reason why behind it being divergent is because the series being generated, the terms are getting bigger and bigger. They're not getting smaller and smaller. So visually, there is no horizontal asymptote I can draw in that picture. It doesn't approach a horizontal value, a horizontal asymptote. Okay, so sometimes a geometric series converges, sometimes it diverges. If it converges, then we have to find what's called the limit. That's the value that it is approaching. This one, you would not be finding that because it diverges. Okay, and on the test, you want to be careful when it asks you if something is converging or diverging. Pay attention if they're asking you about the series or about the sequence that's generating the numbers in the series you're adding up. So if I go back to, well, I'll show you. I'll show you a new example. We'll do something there. So what I want to do now is just look at the formula. That's a sub 1 equals 1 minus r to the n over 1 minus r. I'm just using x for graphing purposes. And I want to think about what would happen for different r values, whether it would converge or whether it would diverge. Okay, so and the first term is just going to be a 1, okay, just to make it simple. So pretend like there's a 1 in front. Right there. Let's see what happens if we make r 0.8. So let's make it 0.8. And in the denominator is 1 minus r, 1 minus 0.8. That is 0.2. So that's this formula with an r value of 0.8. And I've got some extra parentheses now because I don't have fractions anymore for r. I use a decimal. So technically, I don't need 0.2 in parentheses. But it's not going to hurt anything. Okay. So let's go to our table. And look at what happens if we start adding up terms in the sequence. Let's even go up even higher. Let's add up to the first 50. Does it look like when r is 0.8 that the sum is converging or diverging? Yeah?
Diverging?
You think it's diverging? How come?
What's that type? Well, I'm going to type to my I thought because it was increasing values.
It's definitely increasing. Yeah, the y column is definitely going to continue to get bigger and bigger. But is it getting bigger and bigger in an unbounded way or a bounded way? Yeah. Yeah, there is a bound to it. There's a limit. At least to me, it looks like when we get to 50, if you add up the first 50 terms generated by the sequence where r is 0.8 and the first term is a 1, it looks like we're approaching the number 5. We're never going to reach the number 5. Calculator may say we hit 5, but we never really do. Okay, so when r is 0.8, it is converging. Okay, let's try when r is 0.9. Before I do it, anyone have a guess if it's going to be converging or diverging? Yeah?
Be converging because it's still less than 1.
Yeah, so that's what we're getting at. We're trying to figure out what is the characteristic of r to make it converge or diverge. Yeah. So just go to our table. And if you look at what happens when r is 0.9, you can't tell as easily by looking just at the first few terms, because 0.9 doesn't really, when you multiply a number by 0.9, it makes it smaller, but not that much smaller. It's still 90% of the size it was before. So this will converge, but it's a little bit slower to get there. The lower this r value, like 0.1 or 0.2, that's going to make it converge fast. 0.9, it will converge, but slowly. Now, let's do 1.1. Okay, so let's do 1.1 for the r value, and then the denominator would be 1 minus 1.1, which is negative 0.1. Okay, so let's try this one. What does it look like is happening this time? Yeah?
It's going up, very.
Okay, can you give me a little bit more detail?
It's going up in what looks like a unbounded way.
Bounded? So you think there's a limit?
No, unbounded.
Oh, unbounded, yeah. Yeah, it is unbounded. Okay, when you add up the first 20 terms, they add up to 57. When you add up the first 50, it adds up to 1,163. And then the first 75 terms, it adds up to over 12,000. So the sum is continuing to grow without a limit. So this is divergent. And 1.2 is also divergent. So basically what ends up happening is if you multiply by an R value that has an absolute value less than 1. So anything between -1 and +1, that will be convergent. If you multiply by an R value bigger than 1 or smaller than -1, that will be divergent. So you want to think of it as like a picture. This is the zone where things converge, anywhere in that green area. Anywhere in the red area, that's divergent. And then if you use 1 or -1, well, then you run into a problem. If you plug in 1, then you're going to be dividing by 0. So we don't really deal with R equaling 1. Okay. All right, so now I want to think about what it converges to. So here's the formula we had before. S sub n equals A1 over 1 minus R to the n over 1 minus R. So this will converge as long as R is somewhere in that green area. Somebody give me a number anywhere in the green area. Just a decimal. Yeah? 0.4. 0.4. Okay. So now let's say R is 0.4. And we fill that in. And let's add up the first, I don't know, let's do the first 10 terms. So you'd be raising 0.4 to the 10th power. That would be part of the calculation you'd have to do. You get 0.0001 for this right there. Right. Let's add up even more terms. Keep R as 0.4. Let's say you add up the first 50 terms. Well, now you've got 0.019 times and then a 1. What's happening to what's in this red box as n gets bigger and bigger? Yeah?
It's getting, the value is obviously getting smaller as well.
And what is the value in this box approaching?
0.
It's approaching 0. So when n starts to get really, really big, we can ignore this. Because what happens is it approaches 0. So all that we're left with now is a sub 1 times 1 over 1 minus r. And let me write that down. I thought I wrote it. No, I guess not. So what we're doing is we're examining what's happening in this formula as this part, the n value goes to infinity. This whole thing starts to turn into 0. So you're left with this. 1 minus r. And what they usually do is they simplify that a little bit by multiplying a1. Think of it as a fraction. Multiply straight across. 1 minus r. That is the formula to add up infinitely many terms in a geometric sequence. It's actually a simpler formula than when you don't have infinitely many terms. That's more complicated. So infinitely many is a simpler formula. So this is the sum of an infinite geometric series. A sub 1 over 1 minus r. Okay, the only reason that formula is simpler is because this part starts to turn into 0 as n approaches infinity. You don't need it. Okay, so any question on the formula for the sum of an infinite geometric series? Okay. So now let's look at this one. And the first step is to determine, does it converge or does it diverge? And if it does converge, find the limit. Okay. So first question, is this going to converge or diverge? Yep.
Converge.
Yes, it will converge. And how do you know that?
Because R is less than 1.
Oh yeah, R is in that green zone. It's between -1 and 1. What is my R value in this case? Yep, 1/2. Okay, and what's my first term? Yep, 5. And just to write a few of them out, what are you basically doing each time to get the next term? Yep.
Just cutting the previous term in half.
Yeah, you're just cutting the previous term in half. So we've got 2.5. That would be the next one. And let's just do that a few times. 2.5 divided by 2, divide by 2, divide by 2. Okay, so those are the terms that you're adding up. 1.25, 0.625, plus 0.3125, and it keeps going on forever. Okay. Now, first thing I want to do is just look at the sequence of numbers we're adding up. What does the sequence of numbers you're adding up approach? Not the sum of the sequence of the numbers. That's a different question. The sequence itself. Yeah? Yeah. Yeah? 0. The sequence of numbers that you are adding up approaches 0. Now I want to find out what the sum of the sequence of numbers is adding up to, and that's where we use our formula. So we have a sub 1 over 1 minus r. What's 5 divided by 1 minus a half? Yep, 10. That is what the sum of the sequence of numbers is approaching. And if you look at it, it kind of makes sense. 5 plus 2.5 is 7.5. 7.5 plus 1 1/4 is 8 3/4. So if you keep adding up all these numbers forever, you would get closer and closer to 10. So any question on the difference between what the limit of the sequence of numbers is approaching, or what the limit of the sum of the sequence of the numbers is approaching? Important difference between those two questions. Okay, so converging approaches a value, diverging, it's not approaching a value. Limit is the value that it is approaching. Okay, so the limit in this sequence is 0. The limit for the sum of the sequence is 10. So you just have to know those vocabulary because I'll use those on the test. And that's pretty much it for the sum of an infinite series. That's all there is. Okay, so anything else on 11.2 part 2? Okay, so that is the homework for tonight. And you've got about a little over 20 minutes. So you can use the time to try to get a little bit of that done. Tomorrow we'll finish up our last lesson for the class. Okay, that'll be section 11.3. I will be after school tomorrow. I know some people have a field trip on Friday. So if you do have something or AP test or whatever it is, you can come Thursday if you want to make something up. Otherwise, I would try to make sure you come during shop week so we don't have to do it the week of the final. Also, study guide will be available on Friday for the final. Okay. Once you start working on it online, don't submit it. It'll submit itself at the due date, which is, I think, 2 weeks from tomorrow. So the reason I say not to submit the extra credit is because once you submit it, you can't see it. So if you want to use it to study, don't submit it. It'll do it itself.